Mortars and concrete. Cement cannot be used alone for construction work because of its sensitivity to moisture and development of internal stresses. These stresses are capable of developing cracks, and they also reduce the strength of the cement. In order to avoid these defects, the cement is generally mixed with sand and stone. This process of mixing of cement with sand and stone is called as dilution and stabilization of cement. This diluted and stabilized cement continues to gain strength with time when it is used for construction work. As a result, no cracks get developed in this manner. Mortar is a mixture of slaked lime, sand, and water. Therefore, it is also known as lime mortar. The function of sand in the mortar is to make the mass more porous and hard. It also prevents the cracks caused by excessive shrinkage. Mortar is used as a building material. When sand is mixed with slaked lime, it gets converted into a hard mass of calcium silicate. Lime also reacts with carbon dioxide to form calcium carbonate. The reaction goes in the following manner: calcium hydroxide reacts with silica and forms calcium silicate and water, and calcium hydroxide again reacts with carbon dioxide and form calcium carbonate and water. Setting of mortar is mainly due to the loss of water. When cement is added to mortar, it becomes hard and waterproof. It is then known as cement mortar. These mortars are mixtures of cement and sand and other fine aggregates which have a mesh size of below 3 by 16 inch. They are used for bonding in masonry and in surface covering. When limestone containing more than 10% aluminum silicate is burnt, hydraulic mortar is obtained. Concrete is a mixture of cement and sand, where the size of the sand is below 3 by 16 inch mesh size, along with the calculated amount of water. The size of gravel or coarse aggregates varies with the purpose for which the concrete is required. Uh, Common maximum size of coarse aggregates are 0.75 inch or 1.5 inch, but coarse aggregate of even 0.5 inch have also been used. Uh, in case of heavy mass concrete, the size may be even 6 inches or more. The common proportions of cement, sand, and coarse gravel are in the ratios of 1 is to 1.5 is to 3, 1 is to 2 is to 4, and 1 is to 3 is to 6. When the cement concrete is filled in around a wire netting of iron rods and allowed to set, the resulting structure is called as reinforced concrete. Concrete has high compressive strength and relatively low tensile strength. In order to impart high strength as high tensile strength so that it can resist loads which tend to crush concrete, another form of concrete known as reinforced concrete is also used. The reinforced concrete can withstand not only high tensile strength but also the compressive stresses. The combination of steel and concrete produces a structure known as reinforced concrete construction, also known as RCC, which is capable of bearing all types of loads. RCC possesses greater rigidity, moisture, and fire resistance than plain concrete. RCC is easier to make and cast into any desired shape, which can withstand all types of loads. The hardening of concrete is due to hydration of the cement constituents. The process continues indefinitely, but maximum amount of strength as well as hardness is developed during few early days after placement. Therefore, it is necessary to keep the concrete damp for about 7 days in order to enable hydration reactions to go to completion. The chemical reactions taking place between cement and water occur only under favorable conditions of temperature. At low temperature, the rate of reactions in concrete is slow, but it completely stops when the water in concrete is frozen. The process of dampening concrete by spraying water is known as curing of concrete. Hence, curing may be regarded as the process of maintaining a satisfactory moisture content and favorable temperature in concrete during the period immediately following placement in order to allow the process of hydration to continue until the desired properties such as strength are developed due to a sufficient extent. The cement concrete is mechanically very strong, but because of the presence of some free lime, that is calcium oxide, it becomes highly susceptible to chemical attack, especially in acidic water. In acidic water, the lime present in the concrete dissolves and makes the concrete weak in strength. Alkaline waters do not have any marked effect on the strength of the concrete. Moreover, lime is more soluble in soft water than hard water. Consequently, concrete undergoes decay or deterioration in contact with acidic water and soft water. Hence, decay is more quick as the pH of the water decreases and softness of water increases from hard to soft. Sulfates and chlorides present in hard water also remove lime present in concrete. The resistance decreases when concrete is soaked in mineral oils. Even minute amount of sugar present in concrete has been found to increase the setting time of concrete, and as a result strength of concrete is also reduced considerably, especially during first 30 days. Sulfates cause maximum damage to concrete because they react with tricalcium aluminate to form sulfoaluminates, which occupy more volume and hence undergo expansion. As a result, life of concrete is greatly reduced. This can be prevented by eliminating tricalcium aluminate from the cement composition and using cement manufactured from tetracalcium aluminoferrite in place of aluminate. Concrete can be protected by giving a coating of bituminous material which is capable of preventing direct contact between concrete and water. Decay of concrete can also be prevented by coating the surface with silicon fluorides together with zinc oxide, magnesium oxides or aluminum oxides. The calcium fluoride so formed in the capillaries prevents the dissolution of lime in concrete.